Okay, good evening. This is week 8. I finished marking the term test, I think last week on Thursday, and I thought I'd publish it, but apparently you all cannot see the feedback. Okay, it's not your fault. It's my end. I think probably there's a setting that I did not do properly. Okay, so it's my bad. The class average was 51. Last term, the same course have been taught, the class average was 42. Okay, so you guys are doing better. I think the highest was a C. Okay, so I hope if today I cannot get Avenue to learn sorted out to let you view your detailed marking, I will email individually all of you regarding why marks were taken away and what goes wrong. Okay, so there will be a tutorial on June 24th. Is to review the term test and questions regarding the grading. Okay, so the tutorial will be on that. Okay, right. Anyone, any questions? You guys are okay? Anyone, please? I don't hear anything. Okay, so today we are going to go into combined loading. Okay, we are going to go into detail in. So this is real 3D loading of a structure now. Okay, so this is one key objective of this course. Okay, so we are going to analyze structures under combined loading. Okay, so what do I mean by combined loading? So we know, all right, like what you guys have learned before. So under normal stresses, okay, normal stresses induced by axial loading and bending moment. We realize that stress, I'll call it in the x direction, is equal to px over a, right, plus by my over iyy multiplied by z plus by mz over izz multiplied by y. So this is the stresses that has been induced under axial loading and bending moment, normal stresses. Okay, so normal stress. So we already know, and you guys are really familiar with this. And if I have a axis over here, right, and then we have our distance from centroid. So this is our stress x, and this is our y displacement. We have a trend, or we know of a trend that this is how, right, the normal stress distribution will look like, right? So over here, we have negative as compression, and over this side is positive, there's tensile, and over here at the point where y is equal to 0 is known as the neutral axis, where stress x is equal to 0. Okay, so that is stresses induced by normal stress. But because we are doing combined loading, right, there's more than normal stress. Okay, so there are shearing stress. If we look at it, we also have shearing stress. induced, okay, shear stress induced by the shear force. All right. So for this case, we have the shearing stress is equal to VQ over IT, right? So now, okay, I'll write further. Okay, so you can have Vy over IZZ multiplied by Z QZ. Okay, multiplied by QZ divided by T, then plus VZ over IYY QY divided by T, right? Why we have both components together is because it's under 3D loading. Okay, so you have shearing stress in the shear force in the Y direction and shear force in the X direction. So if now we were to construct our shear stress profile now, okay, so we're going to look at our shear stress profile. So this is again our Y, and this is our shear stress. Now this can be Y or this can be Z, okay, right? So now the shear stress profile is different from the normal stress, okay? You will have a parabolic effect, and at the neutral axis, okay? Oh, I should have drawn this better. I do apologize. Okay, so at the neutral axis, this is our tau max at the neutral axis. Okay, something is different now, yes or no, right? Something is different now. So if you look at normal stress at the neutral axis is equal to 0, right? Whereas the shearing stress at the centroid, right, is at its maximum. So how can you look at the materials handbook to select what is the right material for it? Okay, but hold on, there's still another shearing stress which you guys have learned in 2P. So you have shear stress induced by the torque. All right, if it's a shaft, you have a torque, or even a rectangular structure cross section, you can have a torque. So the torque over here is equal to TR over J, right? So now we're going to draw this, right? So if we look at TR over J, so this is your shear stress, and this is your normal stress, right? And because of the trend of the equation, okay, where we have TR over J, so this is your radius. Now, TR over J, there's no positive or negative radius at all. So the trend for this will look like this. Okay, so this is our trend. So if I were to flip vertical, right, this is our shear stress distribution due to the torque. So you can see, right, 3 very different profile. Yes or no? The one on the top is bending moment. The one on the second one is due to the shear force, and the last one is due to torque. Okay, so what is the stress level that you're going to use to select materials? Okay, so what do I mean by that is you have all these. Okay, so you will look at a table like this now. Okay, so now if you look at a table, okay, so this is material properties. You look at the table over here, right? So if you look at a material handbook now, you look at all this. Okay, so it's so easy to read in the sense, okay, the first column is density, the second one is ultimate strength in tension, compression, and in shear. The yield strength in tension and in shear, you got modulus of elasticity, modulus of rigidity, then thermal coefficient of thermal expansion, percentage of elongation. You have all this data, right? Now, if your structure is loaded in 3D condition, which one will you use? Anyone? What will you use? Anyone? Which data will you use? So I have no answer over there. So it depends on how our material is tested. Okay. So if you look at the ultimate strength, right? Everyone knows what's our ultimate strength. So if if I draw a stress strain curve, okay, if I draw a stress strain curve, if I draw a stress strain curve, all right. So this is strain, this is stress. We have this effect, right? Okay. So over here we know that this is known as our yield strength, and this over here is our ultimate strength, right? So if you look at what you see over here, the stresses are in tension, compression, and shear. Tension, shear, not N. Tension, column on tension. So what does this mean? So the material, the mechanical, the strength in most material handbook are under uni directional testing configuration. Okay, so what do I mean? If they say it's tension, okay, so if we have a material over here, this is in tension. Okay, so they pull a cylinder, okay, or a test piece in tension, and then if you look at here, it's in compression. So the next one is in compression. Means the forces, they did a test and they apply force. Okay, so this is P, positive P, this is negative P in compression. Okay, and then you have another value which is shear. So the shear, what they do is they apply a torque. Okay, so that's how they get the shearing stress. Okay, now if we look at a structure, okay, if we look at our problem, so I'm going to give you, okay, this problem. Hold on. Undo.